Swayam Prabha. Digital India. Educated India.
In the last class, we were looking at the friction between the elastomer, the tire and the road. We found that friction is not as simple as what you can see in a metallic friction, but consists of two parts, and we said that that is a mu addition plus mu hysteresis. In other words, we said that the hysteresis of rubber plays an important role in friction. We also looked at the road undulations and how the macro aspect of the road surface and the micro aspect of road surface, both of them are important for tire friction. Now, we will leave this in a minute, for a minute or maybe for half an hour, come back to this, and before that, let us look at what happens as the tire rolls. Now we are from the micro, between the road and the tire, we are going to the macro, how actually the tire, as it rotates, it behaves. We had already seen this. We started this. We said that as the tire rolls, there are three different radiuses. Of course, when it stands also, there are two different things. But when the tire rolls, we said that there are three different radiuses. Of course, one is what we called as, if I remember right or not, the undeformed radius of the tire, which means that that's the tire radius, undeformed radius of the tire. We also said that when the tire enters the contact patch, it has a reduced radius. Okay, it has a reduced radius, and that in between the two, actually, we have an equivalent radius, which I think we called it as, let me call that as RH. I think we called it as H. You could call it as RH. In between R0 and RH, there is what is called as an equivalent radius. Radius, which when multiplied by the omega, the angular velocity of the wheel, gives you the velocity v of motion. As I told you again in the last class, we can look at the velocity of motion of the wheel, the stationary ground, or you can look at it as if this is stationary and the road travels with a velocity of v. Either way, it's fine for us. We will use one or the other as the circumstances demand, but the theory is the same. It's just for understanding purposes, we are looking at it from two different perspectives. Okay. We already saw this, and we added that there are three zones in the contact patch. There is one zone, let me call that between A and B, where the radius is greater than RE. In other words, that is the radius RE, and there is a region where it is greater than RE. Then there is a region where the radius is less than RE, that is this zone. Again, there is a region where it is greater than RE. Right? So there are three regions in the contact patch. So in region 1, since the radius is greater than RE, okay, V that is calculated omega into that R, okay, greater than, let's call the radiuses here as R1, okay, of course it's a function of S, let's just leave that S, let's say R1, okay, that is the changing radius as I move from A to B. At B, of course it is RE, let me call that as C, let me call that as D, okay, and the radius at D is again RE, right. Let me call that between the two, the radius is to be R2, which is actually a function of this length S. Let me leave that for a minute. And let's say that in this region it is R3 and again function of S. So here between A and B, R1 multiplied by omega is greater than V. In this region, R2 multiplied by omega is less than V. And in this region, R3 multiplied by omega is again greater than V. Right? So that gives us a very interesting picture as to what happens in these three regions. So there is. How did we get this result? So what is this R I am talking about, and what are these results? Right? That's the question. Now, as I told you, let's say that this is the R0, which is undeformed radius, right? So we will see what happens to a circumferential element in a minute. This is what we started in the last class. We'll see that in a minute because there were some questions on this. I'm repeating it. So at this point, I hit the contact patch, right? So omega R0 is the tangential velocity at that point, right? So as the points in the contact patch move, right? We also saw how contact patch actually is defined in the last class. So you have to have all those concepts what we taught in the last class in your mind. So as I move from this point to A to B in the contact patch, in other words, as the contact patch moves above me between A and B, that region of the contact patch, the radius is greater than RE. Okay, and here again the radius is greater than RE. Between the two, the radius is less than RE. This is all I'm saying, nothing more, nothing less. So since it's greater than RE, V being omega RE, this region between A and B, R1 omega is greater than V. Similarly, R3 omega is greater than V. In the same fashion, we can say that R2 omega is less than V because R2 is less than RE. So there are regions where the tendency for the thread to slip, okay, will be different. In these three regions, the tendency to slip will be different. Right? On one hand, the thread wants to go, if as I told you last class, if you're going to sit here, okay, the thread wants to go faster in one region, faster, which means it has a tendency to slip. In another region, the thread goes slower, okay, and another region, the thread goes faster. So there are three regions in which the thread head wants to go faster or slower. But let's for a moment assume that the friction is fantastic, and that it's going to stick, and that it is not allowed to go faster or slower because as it hits the ground, it's going to, as I said, it's going to go stationary, going to stand there, it's not going to move. So it is a question of the threads being pulled in one direction or pulled in the other direction. Okay? So here in this region, what happens is that the wheels go slower, so the thread which was, let's put it like this. Let's say that I'm just exaggerating the picture here in this region. Okay? Now thread which was nice like this, let's take a thread at this point. A thread, I am representing it by a stick. Let us assume that that's a thread block. I am representing this as a stick. So here, as it sticks to the ground, okay, that's the carcass. When it sticks to the ground, it wants to go faster, okay, but it is sticking to the ground. So there is a tendency for it to be pulled in one direction. As it comes here, there's a tendency to be pulled in the opposite direction. And when it comes here, there's a tendency to be pulled in the other direction. So let me put that as a force. Okay? Let me pull that pushing or pulling, whether it is going to be pulled like this or like this, we will put that as a force in a minute. Right? Okay. Now, before we go further and go and lie down there were questions as to how actually load is transferred, load transfer in a tire. This is very important to understand. Okay, vertical load transfer. This is a very nice, I would say, concept, physics, that comes into picture as to how actually the load is carried by the tire. A lot of misnomers, so let's understand that, very carefully. Right? There's a tendency to believe, number one, not all of you, I'm sure all of you do not have this kind of beliefs, but some of them, as I see it, yes.
R1 omega, R2 omega, they are all instantaneous velocity at that point.
Yes, absolutely. So in other words, the question is that does the velocity actually change, or in other words, R keeps on changing. So when R keeps on changing, okay, that instantaneous velocity also keeps changing. In other words, amount of slip is not the same. Give me a minute, I will explain this and come back to this question. I know there are going to be a lot of questions, okay, it's very conceptual, okay, so we are going to go very slowly. Right. Before we go into this aspect, let's look at load transfer. We have not talked about how the vertical load transfer takes place in a tire, right? Okay. All of you drive bicycles. Okay, let us first understand how actually the bicycle wheel carries the load. Oh, you see that every day. It looks like it's very simple. What is there? You would say that, okay, that's the bicycle wheel. I'm just putting the spokes, okay, on the wheel. What's there? There's going to be a load like this, there's going to be a load like that, and it's all over. That's the free body diagram, okay, and the wheel is under equilibrium. What else is there to talk about this? Unfortunately, a lot more, because the spokes, as you know, is a very thin piece of steel. Okay, if you subject that spoke to compression, what is that that's going to take place? It's going to buckle. So the spokes are assembled with tension. Okay, they're going to be actually assembled with tension. Right. So when the spokes are not, let's say that they are not on the ground, just take the wheel out, then there's a tension in the spokes which are opposite to each other, and they would cancel each other. Okay, so it's not that the wheel will run away in one direction or the other. They are under equilibrium because of the forces that are inbuilt into these spokes. Clear? Okay. Let's just consider a very simple situation. Forget about all other spokes. Now, this spokes is under tension. Just we'll consider one for clarity. That spokes is on the ground. So there is a compression onto the spokes. So what really happens is that the tension here is reduced. Okay, the tension here is reduced. Let's depict that with an arrow. Okay, that is all is the tension. But this guy who is sitting there at the top, his tension is not reduced. So his tension is high. With the result, if you look at the forces, okay, which are actually acting on the axle, you would notice that this guy is the one actually which is responsible for the support of the wheel. In other words, the wheel hangs from the top, and that's not just pushed from the bottom. So the hanging here, this hanging here is one which holds it, So there are a number of forces. That's the load that's acting, and there is a spokes which has an initial tension. It's a ground. So the equilibrium demands that the whole wheel hangs the axle from the top. This is exactly what happens in a tire. But who plays the role of the spokes in a tire? It is the sidewall of the tire. So let's draw the sidewall. Okay, let's say that that's the sidewall of the tire. Okay, they are, let's say, sitting in a rim. All of you have seen a rim. Okay, and then again it goes like that, and then that's the rim, and then there is a sidewall of the tire. In other words, let's say that that's the tire, and that's the bead, what is called as the bead. Okay, you would have seen that, all those things, and that is this is the tire, right? Now this sidewall is now going to act like a spokes. Here the tension is in the spokes is given when we assemble the wheel. Here the sidewall gets the tension from the pneumatic pressure. Okay, so the pneumatic pressure, in other words, the inflation pressure. You go to a shop and you fill it up, 32 psi is the pressure you say you keep it. So that pressure is what gives the equivalent tension in a spokes to the sidewall, right? So is it clear? That gives the tension. Now let's see what happens. Okay, that's the axle. Let's look at what happens to this whole situation. Of course, the first thing you would say that, look, that's the inflation pressure, that's how it acts throughout. Okay, there's an inflation pressure like this. Okay, acts on the rim. Let's say that it's a tubeless tire. If tube tire doesn't make any difference, that is what is the inflation pressure, and that's the ground reaction. Clear? This is how it acts. The first thing you have to understand is that the load bearing has nothing to do with the compression of the air inside. In fact, this issue was settled long ago in the early 60s. If I remember right, there's a paper in 1962 which very clearly showed that the pressure, the pneumatic pressure, does not vary more than 1%. It's much less than 1%. So it is not that this air, okay, carries the load, right? Air, of course, acts as a cushion. They are the different thing. This gives that springiness and so on. So it is not that which carries the pressure. Then what is that which carries the pressure? In the same fashion as we explained the spokes, okay, if you now look at the side of the tire, pardon me that it's not a very good circle. Now, inflation pressure acting all through, this pressure, now this, so that's how it acts on the ground, right? This, there's a difference between in the tension, again the same fashion here. So that now reduces, on the other hand, this pressure gives more, or this is more than this now, and so the side walls have the tension, okay, to pull the rim, and through which it pulls or gives the reaction to the axle. So in other words, the vehicle load is reacted upon by an upward force, the downward vehicle load, reacted upon by the upward force which comes from the top. Again, as in your bicycle wheel, a passenger car tire or a truck tire or whatever it is actually hanged from the top. It's hanged from the top. It is not that they are supported from the bottom. So the whole load actually goes through this side wall onto this most important component called the bead, okay, which transmits it to the rim, and that gives the force for the rim to support the load. Is that clear? Any questions? Okay. So this is an important concept on how load is transferred or held by the tire. Okay, we will come back to this rolling tire again. This is a phenomenal concept of pneumatic tire, because as it rolls, the whole load, you know, the different points in the tire is now held by different parts of the tire, because this is not a stationary, this is a stationary figure, but imagine that actually it is rolling. Okay, as it rolls, so there are different parts which come and which is under tension and which holds the wheel. So there is a compression tension or a cycle which takes place, which is also responsible for hysteresis. Now let us come back to this figure and let us understand what we meant by slip and what happens here. Now let's say that that's how the wheel rolls, right, and that there is a contact patch which is developed under the road. We have seen that. That's what we had seen that as the reaction, ground reaction. The sum of this, the area under this contact patch, contact pressure multiplied by that is, in other words, if I say that the contact pressure is P, okay, which is a function of x, y, dx, dy, if I integrate the whole thing, okay, is the total reaction of the ground, okay, that we are talking about. Right. As we had seen earlier, this is not symmetric for a rolling tire, with the result that there is an unsymmetric distribution results in a force that acts, which is responsible for rolling resistance. We said that the unsymmetric distribution is due to the viscoelastic properties of the tire. Let's see what happens because of this variation in the radiuses. Obviously, this variation in radiuses causes a lateral force. Okay? So the lateral force in the first part up to A, it's like this in one direction, and then starts dropping and then goes in the opposite direction and then goes up again. So in other words, the lateral force developed depends upon the difference between the velocity of the wheel and the ground velocity. What is meant by ground velocity? We said that we can treat the motion of the wheel as if the wheel is stationary and the ground can move in the opposite direction. So it is the difference between these two that would cause a extension or a compression of these tread elements. It's very important to understand this. Very important to understand that the tread elements can be extended or extended in either direction, I would say. Okay, extended in either direction. Just to before I go here, let us understand this carefully. Let us say that that's the wheel, okay, and let's say that there's a tread element which is sitting. That's the carcass rather. Okay, the treads are blocks which are extending from the carcass body of the tire. Right, they are extending, and they are the ones which are touching the ground. Clear? Okay, so they extend and touch the ground. He is rolling. You can either assume, as I said, he is going with the velocity v, or that's stationary, and this is going with the velocity v. Let us consider two extreme cases. Yes?
So this threads thing, sir, are we actually assuming it or is it actually...
No, it's actually there. In any, we will see that first day we saw that tire, we will again see it in the next class. Okay? You will have tread blocks, okay? And actually you have belts, tread blocks and all that. Okay? For example, if you take a radial tire, you have a ply, and you have belts, and you have treads which are supported on that. Okay, and we will see that again in the next class how it looks like. Okay, we'll take a real tire and we will see it. Okay, so we will do that in the next class.
What is on the y-axis for that first graph?
This is the longitudinal force. Okay. We will come back to this. We will look at this. We will look at the extreme conditions and come back. Slightly difficult concept to understand, but let's try how best we can do this. That's a normal pressure. That's a normal pressure. Okay. Now, let us look at two extreme conditions to understand it, and then we'll extend it to a simple, normal conditions. Okay. Now, let us say that we have applied a sudden brake, right? What happens when you apply a sudden brake? The wheel now won't rotate. Wheel won't rotate, but the vehicle will be moving. Let's say assume that vehicle the wheel is completely locked, but the vehicle is still, say, let's say that it's moving. Right? So, gone, that's gone. So, this would result in the ground moving in this direction as if this is stationary. Okay? So, at this point there won't be any velocity because it's not rotating. Okay? So, the ground is moving in this direction. That is how that tread will be stretched, because he is going this direction. This is just to understand. I said both of them are the same. So, tread is actually stationary there. Let's say the friction is so good that it's standing there, right? And this rotation is stopped. Okay? So, this fellow is going there. What would the tread do now? Tread is now, it's an elastic material, it is now getting extended. So, in other words, there will be a force on the tread, there will be a tension on the tread, right? So, one side, poor guy, one side the road is going to hold him, the other side the tire carcass is going to hold him. Okay? Either side he is held, and this guy is stationary, this guy is moving. So, what will happen to the tread? He will now pull, he is not going to leave the other side. Okay? So, he is now going to pull the tire. Hey, don't go away, I am being pulled here, I am going to stop you, with the result that if you now resolve this force in the longitudinal direction, that would result in a longitudinal force, and that gets depicted as a braking force. So, it is this tension which is now causing that wheel to stop. Okay? Or in other words, that is what is the braking force. Just the opposite happens when it is when we are accelerating. It's easier to understand like that. So, there's a braking force that is generated, right? You can, same concept can be explained as if this is a velocity, okay, and that is moving, this part is stationary, that part is moving, and again there will be a tension, and that will be causing cost in this direction. Okay. Now, the other extreme is during, or other part is during accelerating. In accelerating, okay, there is a difference between this velocity and it will be in this direction, and this velocity at the rim. Let's not, now we understand this. So, there will be a difference in velocity between the two, right? So, with the result that there will be a stretching of the wheel, of the tread, and that stretching would give the force which is the traction force, right? So, one side, stretching in one direction gives the braking force, and the stretching in the other direction gives the traction force. So, it is this stretching, however you view it, is responsible for all the forces that are developed on the tire. So, here we have assumed that there is no slipping of the tread, as if this whole thing is held. Okay. This is just to understand this. When we put this into the vehicle, into the wheel, it's going to be slightly different. Right. Okay. So, in other words, you may argue that why should it stand there? When the forces are more than what the friction can withstand, it will start slipping. Absolutely correct. Right? Okay. Now, let's extend that here first. What is that we learned? We learned that when there is a difference between the peripheral velocity and the velocity of the vehicle, okay, a force is generated, number one. Number two, depending upon whether it is lower or higher, the direction of the force would also be different. This is what we learned. Clear from this? Any questions? Right. So when I extend that concept to free rolling, this is free rolling, and assume that the friction is good enough that there is no slip. Okay, here slip, what we mean is slipping of this. When the force, say there's a tangential force, and the tangential force is higher than the what can be withstood by the frictional force, then it would start slipping. Okay, we'll come back to that figure again. We'll be talking about that figure more often now. So when it hits the ground, so a force is generated in one direction. So all this guy is under tension, okay, in one direction. Now, as he goes from B to C, this part, B to C, the tension that is generated in one direction is now going to be relieved because there is the difference in velocities here would now come into play. They are different. Here one side it is more, another side it is less. Okay, more acting in one direction, less acting in the other direction. So you have now pulled it. The fellow, when he reaches here, he is going to get relieved now. So the longitudinal force that is developed from A to B will be like this. Then it's released. Keeps building. And then again it goes in the opposite direction, and so it goes back to zero. So that when the tread gets up from the tire and goes out, all those forces, longitudinal forces, have to go to zero. Right? That's what happens. All the longitudinal forces, or the longitudinal force, because it is outside the ground. But interestingly, if you look at the sum of the longitudinal forces, okay, this is in one direction and this is the other direction. Sum of the longitudinal forces is not equal to zero, because even in free rolling we have what is called as rolling resistance. So that rolling resistance manifests as a difference in these two. Okay, so if it is A, if the total force that's acting is A, or here, okay, because as I told you, please remember there's a compression tension, the curves are different, so they are not the same, and all that viscoelastic concepts now come into picture here. Because after all, the tread is getting compressed, it's getting relaxed, compressed and relaxed and so on. So all the viscoelastic forces now come into picture, and that the loading curve is not the same as unloading curve. So if there is a force A in one direction, the sum of the forces here in this case, which is behind the contact patch, they have to be A plus a rolling resistance force. So in sum there is a difference, and in other words that results in a rolling resistance force Fr. Now what is the effect of that rolling resistance force? There is, in other words, there is a force which opposes even in free rolling. That is, you are neither braking nor you are accelerating. Okay, it's a free rolling, no other force is acting. Okay, even in that free rolling there is a force which opposes the motion and has to be compensated by a torque onto the wheel. So you neither accelerate nor brake, you need, okay, a force that is acting. That is the rolling resistance force.
By de-rolling, what do we mean? Engine is not providing.
We are not, we will define it more carefully slightly later. Right now we will say that we are neither braking nor accelerating, we are going at a constant velocity. Okay, but we have to define this carefully. We will do that, after some definitions. Right now understand that we are neither braking nor accelerating. In other words, I am not applying a lateral force, longitudinal force. I am not applying a longitudinal force. Okay, so either to brake or to accelerate. So under these conditions, the only force that acts is the rolling resistance force, and rolling resistance force has to be compensated. Clear? Right. Any questions? In sum, as the tread elements goes under the contact patch, it is just not the normal compression alone which works. Along with that normal compression, there are longitudinal forces which also act. That's the sum and substance of what we have been talking about. And these longitudinal forces are not just equilibrated on one side of the contact patch to the other, and they result in an uneven distribution of forces, and that is what we call as rolling resistance. Good. Now let us go and lie down here and see what happens as I roll. As I now start rolling, let me call that, let's say that you're lying down like this. So as I now roll, and as I come to the contact patch, the radiuses are going to decrease and I'm going to get compressed, because after all, I am in a free surface or free stress-free state. I'm just lying there. Okay. As I enter the contact patch, because in other words, I am a part of this circumference, obviously. So as I enter the contact patch, my radius is going to change, so I will get compressed. Right? So in fact, interestingly, the impending contact is felt by me even before. It is not that, so theoretically speaking, we said the radius is the same here and so on. In actuality, the impending contact with the ground is felt by me before. So if my tangential velocity slightly away is omega r naught, so as I approach the contact patch, okay, my velocity now keeps dropping. In other words, I start becoming smaller. Okay, so the velocity starts dropping even before I hit the ground. When I hit the ground, in fact, for a very small distance, I still keep contracting. So you will see, that's the graph you see. So that is the place where I hit the contact patch, but my compression keeps extending till a small region. In other words, till say that point. Let's for a moment assume that there is no slip. In other words, friction is good enough for me to hold. Then usually there is no variation in the velocity, okay, and at the end you would see a small bump of rubber. In other words, the rubber is under compression. This is because the rolling resistance has given me a force there, and that force gives me that extra compression towards the end, an extra compression towards the end, and that results in further drop of my omega r, and then I raise after this, and then I go back to my original velocity. Strictly speaking, this is not a straight line. There's a small variation, as we had seen just now. There's a small variation, okay? But for all practical purposes, people draw that as a straight line. In actuality, there has to be a small gradient. Then there's a sudden dip because of a compression which exists at the end due to that rolling resistance force. Raise up, then go back again. In other words, if you are sitting on the circumference of a tire, and if you are measuring your own velocity, that's how it would vary. Clear? Okay. Now we have to enter into a lot more technicalities. The first question I know many of you have right now is that there is a limiting friction. You are talking about sticking. That's not the reality. In other words, there's a race between the normal force determined by the contact pressure and the tangential force determined by this pulling and pushing. And this is not a constant throughout the contact patch. And whenever one exceeds the other, in other words, the tangential force exceeds mu into n, it's going to slip. Understood? So that is what is going to also play a role here, and we're going to see that, okay, for both braking as well as for acceleration. We'll take one case because the other case is just opposite. We'll take braking, we'll explain this and define what is called as a quantity called slip. In other words, omega r, and what is r is going to play a great role, okay, in our definition of slip. Clear? We will see that in the next class. Remember that the r values are not a constant as you go along the contact patch. We will extend these concepts in the next class and define what is called as the slip. Our next goal after this is actually simple when compared to what happens during cornering, because the cornering, during cornering I have to develop a centripetal force. And the centripetal force is also developed because of this kind of interaction between the rod and the wheel. And these tread elements, when I say tread, it along with the belt and so on, they participate in creating that force. And a combined situation where you have cornering plus braking, you have a tendency to brake when you corner, cornering and braking, then there are two forces that are going to act. In other words, for this quantity called mu into n, there are two guys who are going to compete, or who wants that mu into n. After all, mu into n is the same. So when there is cornering plus braking, then there is a longitudinal force as well as there is a lateral force. Both of them now act, and both of them want a part of this pie called mu into n. So this is combined cornering plus braking. So we'll first look at braking, look at cornering, and then we will combine both cornering and braking and look at how the force actually gets distributed. We'll see that in the next class.